Hello, it's Keith here, and this is lesson 90 of the platform-specific series of my Z80 assembly programming tutorials. We're looking at the SAM Coupe today, and we're going to be looking at adding interrupts and music to our previous example. This is the min-tile example we looked at before. It's currently my best graphical example, the most advanced, and we're going to be adding music to it, and we're going to do it via interrupt mode 2 rather than the simpler interrupt mode 1. Why are we using interrupt mode 2? Well, interrupt mode 1 always calls an execution to memory address 0038, and that's the easiest way of using interrupt, but it poses some problems because of the SAM Coupe's hardware capabilities and limitations. The SAM Coupe uses a 24K screen. Now this is a very large screen, and it can be paged in either at the 0 to 6000 range or the 8000 to E000 range. Either of those can be the visible screen, but the problem with this is that if we're at the 0 range, that means our interrupt handler can't use interrupt mode 1. And if we're at the 8000 range, the interrupt handler at the 0038 address will work fine. But what if we want to use a large amount of source graphics and we want to page in more bitmap graphics and transfer them to our screen? ChibiTracks did this, and it would disable interrupts and page in and then re-enable them and after it had paged out again. So, but on the Amstrad CPC, a missed interrupt will fire as soon as interrupts are re-enabled. On the SAM Coupe, just like the Spectrum, if interrupts are disabled and the interrupt should occur when they're re-enabled, the interrupt is lost, and that means that if we disable interrupts during our graphics routines, the music will start to slow down, almost as if we'd never used interrupts at all. So they don't really help us there. So what we want to do is we want to create an interrupt handler that will work within the block of the graphics area so that we can page the low area to whatever we want, and we can take advantage of interrupt mode 2 and do that. Interrupt mode 2 is a little bit tricky to work with, but if we use the right data with it, we can create a jump block at the E000 range, which will do our interrupts just fine. As an added bonus, we're also going to look at moving the drawing routines out of the low area, which they were in the previous example, also into the E400 range, so the drawing will occur there, and that will mean that the low 0 to 7FFF range, we could page out and page in new graphics if we were required. So that's going to be there as an added bonus. So that's what we're going to be looking at today. Now, I should point out there is an alternative I've thought of, but I don't think it's as convenient. Interrupt mode 2 is a pain to get working, but once it's working, it works perfectly stably. The alternative would be to put an interrupt handler in every single one of the banks we might want to page in with our extra graphics data, but this will cause some difficulties depending on how your graphics routines are working with regards to you're always going to need to allocate at least part of that bank, and that could make calculating the bank numbers. The way I was going to do it, you see, is I was going to use the high bits of the tile number, and using part of the bank would make the calculations more complicated. So I think interrupt mode 2 is worth considering, but it's not the only way. If you want to page in multiple banks, putting an interrupt handler in every single bank at 0038 is also an option, but it's not the one we're going to look at today. Anyway, it's all a little bit confusing, the theory of it, but the practice isn't actually too hard. You can literally copy paste the code I've got if that's what you want to do. Anyway, let's just quickly discuss how interrupt mode 2 works and what we have to do to trick it into doing what we want. Now, interrupt mode 2 is basically designed that the hardware that causes the interrupt will pass a single byte, and this becomes the low byte of an address. The high byte is provided by the I register, which we've probably never used before, and those two are combined and they become an entry in a vector table. This is a table of 16-bit addresses. So that resulting address is used, and then an address is loaded from that, and that is the final address that is called. Now, I'm not sure about the SAM Coupe, but on the ZX Spectrum we couldn't actually predict what the byte that was provided by the hardware would be. It was pretty much random, and so what we would do is we would write a single byte 257 times, so that whatever that byte was, the same address would be loaded and the same address would be executed. Now on the ZX Spectrum, we were using the address 8181. However, for the SAM Coupe, that's not going to be convenient for us because the screen is actually at the 8000 to D/FFF range. So we're going to use the E000 range onwards, and we're going to use the address E1E1 for our actual interrupt handler. So that's the theory of it. As I say, interrupt mode 2 is a bit weird, a bit annoying, but if you use this template code, it will work just fine for you, and you can just forget about it almost. So that's what we're going to do. Okay, so what do we need to do to get interrupt mode 2 to behave for us? Well, the first thing we need to do is we need to create the vector block, the 257 byte block, and so that's going to be at E000, just after the screen memory. We're going to write the value E1 257 times. The first time we're doing manually, the rest we're doing with an LDIR. So that has set up all of the vector jumps to the final address of our interrupt handler, and we're copying our interrupt handler here. This is currently in the 0 to 7FFF range, but we're copying it to memory address E1 here because that's what will actually be executed when an interrupt occurs. So that's what we've done there. What we then need to do is we need to load the I register with the value E0. We're doing that here. We're taking advantage of the fact that A equals E1, and so we're converting it to E0. That's because the vector table is at E0, the interrupt handler is at E1. So that's what we've done there. So that's created all of the preparation we need for our interrupt handler to execute correctly. As I say, the theory is a pain in the ass, but the actual practice is fairly straightforward. You just need 257 bytes, all of which are the same number, and that number needs to have an interrupt handler at it, and that's all it takes. We then set interrupt mode 2, enable interrupts, and that's it. Interrupts will fire. The memory address E1 will always be called, and that just needs to be our interrupt handler. So let's take a look at what our interrupt handler actually is in this case. Well, here it is. Okay, now this is actually going to be relocated to memory address E1, but that's not actually where it is in the code at this point that you're seeing it. When it's assembled, it's not at that address, and the important thing to notice there is this is going to be relocated. Now there's two things we can't do with relocated code. Well, there's one thing really. We can't use absolute addresses. That means no JP and no call. We can use JR because JR is relative, but JP is an absolute address, and it will be the incorrect absolute address when this interrupt handler starts. But wait, I hear you say, what's that call doing there? That is an absolute call. That's calling that function at that address. And if we relocate this to E1, that won't be there. Well, it will be by the time that calls, because what we're doing here is we're paging in the original bank, and then we're paging out the original bank back here. So when this command runs, that command will be at that address as it is assembled there. It's only before this that we can't use absolute calls. So what are these doing? Well, 250 is the bank selection register for the low area 0 to 7FFF. What we're doing here is we're reading in the current value, pushing it onto the stack. We're then restoring it at the end so that when the interrupt handler ends, whatever bank was paged in will still be paged in. But in between here, we are paging in the original bank with the music and the music playing software in it. So we're basically saying, well, we don't know what the low bank was when we was called, but it's now going to be what we need it to be. We'll do our job, and then just before we finish, we'll page back in what the original calling routine wanted, so that when the interrupt ends, everything carries on as it did before. So there we go. So that's what we're doing there. So the only final thing we've got here is we're having to set up things. We're setting up the VRAM bank. This is the displayed VRAM here with port 252. Now, the other thing that we're going to briefly discuss here is I've added a sort of another little bonus part to this, which is, as I say, really the reason we would want to use interrupt mode 2 in this case is because we might want our graphics drawing routines to be in the same bank as the VRAM destination, so that we can page in other bitmap graphics or other source bitmaps into the 0 to 7FFF range. So what we're going to do here is we're going to transfer the source drawing routines into that memory address of the VRAM bank. So what we've got here at E400 is actually some code, and I've created a jump block. Now, I don't think this was actually needed in this case, but if you're messing with relocating code and if you're assembling your project in multiple parts, a jump block makes things a lot easier. You just call the address in the jump block, and then the contents of what happens after that are all handled by that code independently. So if you need to relocate things, if you are compiling a binary and then importing that binary later into the final program, this makes things a lot more straightforward, because as long as this part doesn't change, what happens within the rest of the code doesn't matter so much. So I've created this jump block here, and all of these are basically exactly the same as they were before. Now, they don't actually use any paging because this example is so comically trivial it doesn't need any. But what I'm envisaging you would do here is if you were using a very high base tile number, you would want to page in the correct bank for that tile for that bitmap data. But as I say, this example is far too trivial to need it. What it does need, however, is it needs the code to copy from the current source bank to the actual VRAM bank. Now, in my example, I'm using banks 14 and 15 as the VRAM. The banks are 16K, but they're paged in 32K blocks. So I'm paging in 14 and 15 is the VRAM here, but when the program is loaded, the program is 64K or so, and the system will automatically load that into consecutive banks, but that is actually being loaded in to banks 1 and 2. So that's not the VRAM bank, and I didn't want to just use the bank 2 as the VRAM. I wanted to use the very high banks for VRAM. So what we're going to do is we're going to transfer our program, our graphics routine, from the bank that it's been loaded into, bank 2, into the final bank. And so what we're doing here is we're paging in the second part of our program here, and that we're paging this into the high memory area, and that's so that we can execute it because our current running code is in the low memory area. What happens next is we branch to this copy code routine, and that is part of our jump block. So that will actually cause a jump to this copy code. Now this is actually running at the correct memory address, so it hasn't been relocated. There will be a huge gap in our code here, in our compiled binary here, but that doesn't matter for this example. That's just fine. This would actually be other parts of our game code. What this is going to do is it's going to page in the VRAM bank into the low area 0 to 7FFF, which is fine because we're no longer running at that memory address. We're running at the E400 range onwards. We're then going to copy our source data from E400 onwards to the equivalent address within that bank 15, within the VRAM bank. And so what we're going to do, because that's actually in the wrong memory address, it will be in the 8000 range, but it's currently in the 0 range. So we're subtracting 8000 to get to the equivalent destination within that bank. We've paged that bank into the low area here. We're transferring our code into that bank here. We're then paging in the first bank of our program code here, and then we're returning here. So this has transferred our video routines into the E400 range of bank 15, our VRAM bank, and that means we can now draw from that VRAM bank with the code in the VRAM bank to the VRAM bank, and we can page whatever we need into that 0 to 7FFF range. I know that's all a little bit complicated, and the simplest solution to avoiding this kind of complexity is simply make a small game that doesn't need bank switching, which is something I have recommended on several occasions. But if you're going to create some monster impressive game, you're probably going to have to start thinking about bank switching, because that's the only way you're going to be able to have complex graphical animation or multiple levels. You're going to have to start thinking about something like this. So I thought we'd discuss it here. Anyway, what about ChibiTracks, the music software? This is my free music player and my ChibiTracker music editing software. How does that work? Well, briefly, all we need to do to get this working is we need to allocate some memory and we need to initialize it. So it uses around 128 bytes. It varies slightly depending on the platform. So here we're putting it a memory address 7800. We're enabling two functions here. Allow speed change allows the speed of playback to be altered in real time. This isn't an optional thing. You can pre-multiply the speed, which means that the binary export actually has the speed already applied to it. That reduces the flexibility, but it makes the playback faster, and you can make the program smaller by disabling this option here. The advantage of being able to change the speed is if you're playing your game on 50 and 60 hertz systems, there will be a speed difference in the interrupts, and so you might need to be able to alter the playback speed of the music to make the music sound the same on both systems. If you were doing a game like Super Mario, where the music speeds up as the player is running out of time, you won't be able to do that if you've pre-multiplied it, but allow speed change will allow you to do that. Allow relocation is to do with the binary. The binary has addresses built into it, the music binary. If you allow relocation, then whatever address it's finally loaded to, it will play fine. If you disable that, it makes the player a little bit smaller, but the export, the destination address when you exported the binary from ChibiTracker is the address you will have to play it from. And then finally, we're just defining a few bytes here for the various attributes of our actual song here. So these are all being defined as the various entries that the code needs to work with, and so these are just being defined for the player to work correctly. Now, when it comes to starting the music, it's pretty straightforward. All we need to do is load the address of the song we want to play into HL and load that to Songbase, and then run start song. That initializes the song attributes. The other thing we need to do before that, though, is we need to start the sound driver for the platform. So we run Chibi Sound Pro init here. Now these all point to various included files. Where are they? So here is the actual code that we need. We need the platform-specific sound driver, Chibi Sound Pro. We need the tweener. These are used for fractioning and calculating the music, and then the notes. Sorry, and then we need ChibiTracks, which is the player itself. We then also, of course, need a binary song file. This one is actually an ASM file. Chibi Tracker, because I'm weird and do things like this, the actual raw music file is ASM, and it will actually assemble in Z80. You can also export a binary, so either will work just fine. There's a binary file there, that's an ASM file, both will work fine. And so we're actually using a raw ASM file in this case. Our interrupt handler, all it needs to do is run ChibiTracks play. That will update the music and the sound. It uses the AF, BCD, HL and IX registers. It doesn't use IAY, and it doesn't use the shadow registers, and so that's why we've got those choices made there. And that's all you need to do. Chibi Tracker, the music software, ChibiTracks isn't the best music player. Arcos is better. However, Arcos has a more limited range of supported platforms, at least last time I saw. I have written some conversion routines that will get it working on a few others, but I've found it in these days easier to actually write my own music player. And so that's what I've done, and that's what ChibiTracks is. It's free, it's open source. You can go on the website and download it, and also the source code for the tracker and things, and do whatever you want with them. As I always say, you're welcome to use all these things in any of your own projects in any way you can. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.